marginal cost at Bulgaria and Moldavia, and that this is the result, $19 and $35. Okay. And the interesting part here is that the revenue of the Bulgaria power plant is, how can we compute? This marginal cost times the total generation, this one. So this time that gives you that. And the expenditure of Bulgaria is that the demand is 500 megawatt. So 500 times that gives you this number. Okay. So for each country, we can compute revenue and expenditure. No, same for Moldavia, revenue and expenditure. So the total revenue of two countries, the power plants in two countries, is this much, and the total expenditure from the customers is the sum of this and that. So we have the difference. So I ask you, where does difference come from? So where does this difference come from? So the answer is in the next slide, right? So, okay, winners and losers. I already talked to you. The winners are the Bulgarian generators because they can sell it at a higher price, and the Moldavian consumers because they can buy at a cheaper price. But the losers are the Bulgaria consumers because they need to buy the energy at a higher price, or the Moldavian generators because they need to sell it at a cheaper price. Okay. And when congestion happens, the congestion in the interconnection reduces these benefits. So let's talk about the difference. The difference is called congestion surplus. Okay, so because of the congestion, we are experiencing the difference between these two. Okay, so infinite capacity, no congestion, they are same. But because of congestion, we have some difference. That is called congestion surplus. And let's compute that. First, the consumer payment. By the way, if you are not quite comfortable with, okay, this is the case when there is no congestion, and when there is congestion, no. The power flow from B to S is limited by 400 megawatt. So the maximum power generation of Bulgaria is just 900 megawatt, and the maximum generation of Moldavia is 1100 megawatt, right? You remember that? And using the marginal cost formula, no, it was given. So 900, 100 megawatt. So the marginal cost of Bulgaria and Moldavia were computed. Okay, so nothing fancy here. So consumers payment. Pi b, the price at Bulgaria and the total demand 500, and the price of Moldavia and the total demand 1500. You can compute. The producer's revenue is also the price and the power generation. Price and total power generation. So total power generation of Bulgaria is local demand plus the power flow from B to S, right? Similarly, DS minus FPS. So you can compute all of the things. So the difference between this consumer's payment minus producer's revenue, that is called congestion or merchandising surplus. So this is just arithmetic. This minus that. Yeah. So yeah, same thing. Minus that. So rearranging the term, pi s, pi b, and yeah, this is FPS, this is minus FPS. So factor out that part, then you have that one. So condition surplus is the multiplication of the price difference between two countries and the power flow from country B to country S. So what? You can consider two things. When this is 0, condition surplus is 0. That's the case when we have infinite capacity line, right? Or this is when this is 0, that means no, 0 capacity. So we have two separate competitive markets. Okay. In both cases, this condition surplus is 0, R0. But no, in the intermediate part, we can observe this kind of curve. So yeah, condition surplus is plotted as a function of the power flow from Bolduria to Sildavia. Okay, so 0, two separate markets, 933 infinite capacity line. So single big market. And the example of 400 is here. So you computed this value and that value, and we observed the difference. That is called condition surplus. So it looks like, yeah, consumers pay more than the generators can receive. Then where is the money? Where does the money go? Where does the money go? The money goes to independent system operator. ISO collects that money. Okay? But no, producers are happy, consumers are happy because we already computed the nodal price. And using the price, no, the transaction happens, right? So consumers pays at the price. Generators get paid at the price, right? And the difference is collected by ISO. So this condition surplus is collected by the market operator in pool trading, and in this case, no, ISO. But it should not be kept by market operator in pool trading because it gives a perverse incentive. Perverse means no, distorted. So yeah, ISO can make money because of condition surplus, but that's not the purpose of the concept of condition surplus. ISO is an independent system operator, and we assume that they do not earn money by operating this system. Their role is just to make the transaction happens and power flows accordingly, satisfying the constraints, right? So even though they can get money, they cannot just keep it. What I'm saying is they need to use it, increasing the capacity of the line and maintenance of the network. Okay, so please do not consider this is the profit of ISO. They should use that to maintain the power systems. And also, maybe some other guys think, hey, that should be returned to the network users, the consumers and the producers. But you know, that's not good either, because then that would blunt the economic incentive provided by nodal pricing. What is the economic incentive provided by nodal pricing? What it says is when congestion happens, it affects the price, and because of the price difference, that comes from the economy and the optimal power system operations. So when there is nodal pricing and there is a difference, but you know, this condition surplus is given to the consumers and generators again, then that's not good. I'm not clear what I'm saying, but you know, we will see. We will see what I'm saying, because you know, we will talk about this nodal pricing on and on again. Okay. Any questions?
라인 이미지 400메가와트였을 때 그거 뭐냐 마켓 그 인피니티 라인에서의 그 서머리 표를 비교해 보면은 그 트랜스미션 라인에 리밋이 없을 때 그냥 가정했을 때 가격이 저렇게 마켓 이퀄리브리움에 도달해서 24.33달러로 나오고 그래서 그 컨디션이 고렸을 때는 저렇게 두 나라가 다르게 나오는데 근데 어떻게 보면은 세퍼레이트 마켓을 비교해 봤을 때 볼두리아에 있는 그 사람들은 15에서 24.33으로 오른 것보다 19달러로 오른 게 좀 더 낫잖아요. 반대로 뭐 실다비아에서도 어쨌든 감소가 되긴 하는데 어쨌든 감소가 되긴 하잖아요. 43에서 35로 43에서 24.33보다는 그래서 뭔가 맨 처음에는 라인 커피시티가 있는 게 좀 안 좋은 좀 약간 제약이 있는 걸로 좀 생각을 했는데 근데 어떻게 보면은 저 두 나라 다 만족을 하는 그런 효과도 있는 걸로 좀 보여지는데 이 케이스에 대해서 생각하는
Good question. So, yeah. So this is about fairness. Okay. So when you think about this expenditure, the total expenditure in this case is lower than that. Okay. So the total expenditure is 48,000 and 62,000. So anyway, in this case, the social cost increases. Okay. And then the total revenue is also increased, but anyway, the total cost increases. But that is, you can say that is at the sacrifice of the people in Bulgaria. So from fairness perspective, you can say, that's not quite good. No, the people in Bulgaria are penalized because they need to buy energy at a much higher price, right? So congestion can reduce the gap. Very, very good point. Any other questions? So this is not trivial, and the concept of node pricing is very important in operating the power system, because here we are only considering these two nodes, two countries. They are connected by a line, but in real power networks, if the network is really huge, in the United States or in the European countries, we have many buses, thousands of buses, and some lines are congested. But suppose that the people here, there are a lot of people here, so that means their load demand is very high, but the cheaper generator is here. So maybe if we want to deliver this energy from here to there, then you need to use some power line. But this line, the capacity is low, so this can be congested. Then if they want to use these power sources, then they also need to pay the congestion fee, or they need to buy the transmission right. Okay. So the concept of nodal pricing is the efficient, optimal use of power system considering the network constraints. Okay, so if somebody wants to use the cheaper energy, but when congestion happens, then they need to pay for that. And the same concept is also considered in P2P trading, and that's the topic of Hing is doing now, right, Hing?
Yes.
Yeah. Okay, so and fairness, when we talk about fairness, it is always not quite clear, because fairness depends on the people's perspective. It's very tricky term and political term. Okay, it's being recorded, so. Okay. So, here the ISO runs the market, and this is the simple case, and the real case, the centralized trading in larger networks. So ISO runs the market, So you may be confused. ISO or MO, they are used interchangeably, and the reason is because ISO behaves like MO in current power system. But maybe not in the future. No, it changes. So here, ISO and MO are used interchangeably. So ISO receives offers from generators. This offers means the marginal cost, the bidding, okay? And also need to forecast the load at each node and need to dispatch the generators at each node to meet the total demand of the network, considering the congestion, the power line limit, and also wants to minimize the total generation cost, including the power losses. So solving that kind of problem is called optimal power flow, OPF. So this OPF is like a holy grail of power system. So if you know how to solve OPF in all cases, then you will be the winner of the power system. But the thing is, OPF problem is a non-convex optimization problem. But for very limited cases, we know that this is convex optimization problem. And the example is for the distribution network where the topology is a radial structure, the tree topology. But in general case, the transmission network has a loop that is called mesh network. So mesh network versus tree network. Tree network is a radial structure. Tree root, we can have only a single parent, not multiple parents. Okay? By contrast, mesh network, any kind of connectivity is okay. And in that case, OPF is non-convex optimization problem. But people are studying, including me, and many new techniques are being developed these days, including using deep learning. So that's the paper Minsu circulated yesterday. Okay? So anyway, the job of OPF is to determine the price of electricity at each node, LMP, the nodal price, and the generation quantity of each generator at each node. So the generators are paid the price of electricity at their node based on LMP, and the consumers also pays the price of electricity at their node at LMP. Okay? So in Korea, do we use LMP or not? No. We are not using LMP yet. Okay? But maybe later that can be used, because we are already experiencing congestion in some line. A lot of renewable generations are from southwestern part of Korea, and a huge demand is focused on concentrate in Seoul, Gyeonggi area. So congestion happens a lot. So maybe you guys live in Seoul. You may need to pay higher price than the people live in Jeollanam-do or Jeollabuk-do or Jeju-do. Actually, Jeju-do price is higher than here. So yeah, okay. But then people are not quite happy. Why do we need to pay more? Okay, so they don't want to pay that. They think that's kind of a tax anyway. So it's a complicated political problem. And you are voters. You can express your idea in the election day, right? That's why you need to vote as a citizen. You know what I'm saying? Okay, so let's talk about OPF, optimal power flow. So here in this example, we have a network. There are 4 buses. So generating units and loads are not all connected to the same bus, but they are connected based on this network. And when we talk about economic dispatch, this terminology, economic dispatch, ED, does not consider network constraints. So when we talk about ED, we assume that all the generators and the loads are connected in a same bus. Okay? So the economic dispatch may result in unacceptable flows or voltages in the network, right? because they don't consider network constraints. So yeah, OPF example, 2 bus case. We have bus A and bus B. They are connected by 2 lines, and the maximum flow on each line is 100 megawatt. So the capacity limit is 200 megawatt in this case. And the generator at bus A is more efficient than the generator of B. Marginal cost is $50. Marginal cost is $100. Okay. Then the example is load here is 100 megawatt. Load there is 200 megawatt. And yeah, so totally 300 megawatt. And yeah, we don't know the maximum capacity of generator A, but anyway, so if a generator A makes 300 megawatt, then that's okay, because 100 goes there, goes here, 200 megawatt goes there, and no congestion happens. Okay, so the solution of this trivial economic dispatch is, it generates 300 megawatt. That generates 0 megawatt. And yeah, 100 megawatts each. So this economic dispatch solution is acceptable, trivial case. So let's see another example. This is unacceptable economic dispatch solution. So suppose that this load is increased pretty much. So total load is 500 megawatt. And we know that this generator is cheaper than that. So first, if you think, hey, what about these guys generate 500 megawatt, the case, then see what happens. Yeah, local load 100. So 200 and 200. But we already know that it is over the maximum capacity limit, right? So the resulting flows exceed their limit, and this economic dispatch solution is not acceptable. Then what can we do? Yeah. Anyway, we need to use this generator. And in this case, very simple example. So if it generates 200 megawatt, then it covers 200 here. So only 200 megawatt need to come from there. So 100, 100. So this is okay. It satisfies the constraints. So in this simple case, the solution of the economic dispatch can be modified easily to produce acceptable power flows. And if you want to solve it mathematically, you can think about this kind of constraints. Something like, so this is the generation minus load goes to there. So there should be less than or equal to the line limit, 200 megawatt. And then, yeah, you can determine the power of that. And anyway, the sum of A and B should be same to the total load, right? So total generation should be equal to total load, but we need to satisfy this constraint. Okay, so you can solve that. This is 2 bus example, and let's go to 3 bus example. By the way, you should be able to draw a circuit diagram for this. This is a single line diagram, but yeah, we will use this. But you should be able to draw a circuit diagram for this 3 bus case. Think about it. Of course, you will not use that because this is much easier. But I hope you to understand, yeah, how it is related with the real circuit. This is single line diagram, as I told you last time here. Okay, 3 bus example. Bus 1, 2, 3. 2 generators, A and B. This is the load, 450 megawatt. And let's assume that generator A is much more effective Then generator B, no, marginal cost is $10, this is $20, maximum capacity, that, 390 and 1500. Okay. So, economic dispatch, we don't care about the network. There is totally 450 megawatt. Then the way to satisfy this demand with minimum cost is to use the cheaper generator as much as possible up to this limit. So the amount of generation is 390 and the rest of the load should be covered by the generator at B, right? Simple. But yeah, so let's see. So 390 and 60. Let's see what happens. And yeah, this is the physical constraint, 200 megawatt, 200 megawatt, and 260 megawatt. And just for simplicity, assume that all lines have the same reactance, actually same impedance, but no, in this kind of analysis, we ignore the resistance component, so only reactance remains. Okay. Then do this injection result in acceptable flows? How can we compute that? Easy, in the sense that, this flow, some of the power flow follows this route, some of the power flow follows that route, and that is governed by the physical law. Okay, so the impedance, reactance of this line is half of that. The length is twice, right? So the impedance, reactance, this is when this is 1, this is 2, then the ratio of power splitting is 2:1, right? Based on Kirchhoff law. Kirchhoff law is called Kirchhoff law in America. So yeah, Kirchhoff. Kirchhoff, that's the pronunciation in Russia, but American reads that Kirchhoff. Okay. Anyway, based on Kirchhoff current law and Kirchhoff voltage law, we know that the power is inversely splitted depending on the reactance. So, yeah, this is the case. 2 injections, and this is the load. And to analyze it, we want to use the superposition principle in power network. So power network can be modeled as a linear system. So when we deal with linear system, we can apply superposition principle. That means we can see this is a sum of 2 different cases and just add them. So yeah, because we assume a linear model, superposition is acceptable. And the way of splitting this is to consider the injection of this part and the injection of that part. Okay, so when 390 megawatt is injected, the power flows that way and that way, and so 2/3 of power flows on this line, and 1/3 of power flows on that line because of the impedance ratio, right? Anyway, so that part and that part, so 390 and 60, and the sum of these two makes that. So in this case, we can compute the power flow. In that case, we can compute the power flow, and just sum of them gives us the power flow of this network. Okay. So, yeah, the first case, that one, FA and FB, they are splitted 2:1, right? So, yeah, the sum of that is 390, and the ratio is 2:1, so 260 and 130, right? And then the second part, 60 megawatt is also splitted, And again, here we assume that the reactance of this line, that line, that line are all equal. So the impedance of that is half of the total impedance on this line. So the power is split again, 2 to 1. So 40 megawatt and 20 megawatt. Yeah, so 40 megawatt and 20 megawatt. And that. And sum of these two gives you the solution. So the sum of that is, on this line, 130 minus 20, opposite direction. So that's 110. 260 plus 20, yeah, so 280. 130 plus 40, so 170. So what? The problem is, actually, do you remember the maximum power flow limit of this network? We assume this power flow limit, 200, 200, 260. So, and the generation amount of that is computed from economic dispatch perspective, ignoring network constraints. And now we need to check that. Yeah. So maximum 200, maximum 200, this part is okay. But no, maximum 260, so overflow. So what's wrong with this overflow? Yeah, this is the maximum limit, so we cannot over that, but what happens if the power flow exceeds this limit? Physically, what happens? Yeah. Actually, there is an ohmic resistance on the line. So this kind of limit is considered that. So when there is more power flow than the limit, then this line becomes hotter and hotter, and the line sags. Okay, sags means it's like that. And then sometimes, there is a tree, and the sagged line can touch the tree, and then fire can happen, and then just this line can be cut. Okay, so satisfying this maximum flow limit is important. But for very short duration of time, it can be violated. Not recommended, but for some small period of time, it can be violated slightly. I don't want to say how much and how long, but similar thing can happen for the transformer. Every transformer has its maximum limit, but you can use it over that for a short duration of time. Of course, then during that period, this transformer can be damaged. Okay, but anyway, all of this are based on the physics. And anyway, so yeah, it's about money. When we use the transformer over its limit, it may shorten the lifetime of the transformer. That incurs additional cost. But if we can do that, but when we do that, if we can save much more money from the generation side, that may be acceptable. You know what I'm saying? So the constraint in power system is not quite hard. I want to say it can be violated for some very small percentage for some duration of time, but no, that may incur additional cost of maintenance, replacing cost. So if you think all of this, you can optimize how much I can violate. You may think about that, but I don't recommend you to do that. Just that's the constraint. You can solve optimization problem mathematically, but in reality, that's not always the case. That's what I want to say. Okay, so here, anyway, yeah, 200 megawatt is over the limit, so we need to reduce that. How can we do that? Well, intuitively, we need to reduce the generation here and increase the generation there. Then how much? So let's think about that one by one. So we must use a combination of reducing the injection at bus 1 and increasing the injection at bus 2 to keep the load generation balance. Anyway, the total generation should be equal to the total load. So when this is reduced, they should be increased. And decreasing the injection at bus 1 by 3 megawatt. No, the power is splitting 2 to 1. So 3 megawatt decrease means 2 megawatt decrease here, right? And increasing the injection at node 2 by 3 megawatt. Why 3? For easy calculation. 3, then the power is splitting again 2 to 1. So 3 megawatt increase means 2 megawatt increase. Sorry. So okay. Yeah, for this line, 300 megawatt increase means 100 megawatt increase. Power is splitting 2 to 1. Okay, so for every 3 megawatt increase, 2 megawatt decreases and 1 megawatt increase from here and there. So a combination of 3 megawatt decrease at node 1 and 3 megawatt increase at node 2 means, so decrease by 2, increase by 1, so decrease by 1, right? 3 megawatt increase, 3 megawatt decrease and 3 megawatt increase implies 1 megawatt decrease here. Okay, and so we need to reduce 20 megawatt. So we need to multiply that by 20. So 60 megawatt decrease and 60 megawatt increase. This is just for easy explanation. Well, you can put minus x plus x, splitting and satisfying the constraint. You can solve that by hand. Okay? But without using equation, we can explain this way. You know what I'm saying? Yeah, so to achieve 220 megawatt reduction, we need to shift 60 megawatt from here to there. So that is this one. So 390 is reduced to 330, and this is increase from 60 to 120. And again, using the superposition principle, we can check whether our calculation is correct. So 330 splitting 2 to 1, 220, 110. This is the load, and 120. 2 to 1 splitting 80, 40. So sum of these two gives you this line, 110 minus 40, so 70, and 220 plus 40, 260, 110 plus 80, so 190. So this is the result, and this is same to the limit. So we are okay. Intuitively, you know how to compute, how to make the infeasible economic dispatch to feasible one. Any questions? So far, so good. Okay, so we have a few comments. This OPF solution is more expensive than economic dispatch, obviously. Why is that? Yeji? Why OPF solution is more expensive than economic dispatch solution? Why? Hiju, why? What are you talking about? 딸랑딸랑. 민재?
그 로드는 똑같을지라도 물리 자체학 조건까지 고려해서 그 양만큼 더 보내야 되기 때문에 더 비싸요.
Okay, so Bolduria, Silvania. So any opinion from Silvania? So why OPF solution is more expensive than economic dispatch solution? Simply from optimization perspective, just one answer, just one line.
제약 조건이 있어서.
Yeah, same objective function, but no, OPF has a constraint. It does not have constraints. So when you have optimization problem and when you have more constraints, then the cost increases, obviously. When you have less constraint, you can find a better point, right? So, in the case of economic dispatch, marginal cost $10, $20, so 390, 60, so this is the total cost. But in the case of OPF, we need to satisfy the constraints. So 330, 120, this is the cost. So the difference between these two, 600, is the cost of security. So the constraints on the line flow is satisfied exactly. Yeah. And also, if we reduce the maximum limit further, then the cost goes up more. Because when you have tighter constraints, then it increases the total cost. Okay. Here, we are based on ad hoc method to solve this problem intuitively and graphically. But in practice, there are systematic techniques for calculating the sensitivity of line flows to injection. That means when you inject at this node, then how does it affect on other lines? That is called sensitivity. When you inject this much, then how much all the lines are overloaded or underloaded based on that. So that's the sensitivity. And these techniques are used to generate constraint equations that are added to this optimization problem. So currently, power system operators use some kind of commercially available optimization solvers. But the problem is, in real power system, again, this is non-convex system, so we don't know the optimal point. Just we operate that at acceptable cost. Okay. That's why we need to study this for more and more. Okay, let's move on to another example. Pool trading in 3-bus system. Actually, this is the example in your textbook. Your textbook starts from here. The same principles are used as we discussed before. So in this case, we have, again, 3 buses, and there are 4 generators, A, B, C, D, and they have their maximum capacity and different marginal cost. So the most expensive one is this one, and the most cheaper one is that one. Yeah, this is the cheapest with the highest, largest capacity. And the information of reactance is, maybe we need to refer to that further. A, B, C, D, load 300 megawatt, load 15, 60 megawatt. 1, 2, 3. 1, 2. Wait, 0.2. 1, 3. 0.2. 0.1. Okay. So, in this case, the total load is 50 plus 60 plus 300, so 410. And in the case of economic dispatch, we don't consider network constraints. So the way to minimize the total cost of meeting 410 is the combination of this. So using this, the cheapest one at this maximum rate, And then the second cheapest is that one. So that's 285 plus 125 becomes 410. Yeah, so this is the economic dispatch, but we need to check how the power flows and whether that violates the maximum capacity limit or not. So that's why we need to compute this. So to compute that, actually, so this is 410 minus 50 is 360, and 60 load, and 300 at this. So using superposition principle, well, there are many ways to split this into two, right? Just A plus B equals C. But it is important to split in a way that it gives us some intuition. So that is the case because we have a 60 here and 360 there, 300 there. So 300 plus 60 would be good to split this system intuitively. So 300 is split here like that. So impedance 0.2. This is 0.3. So 0.2, 0.3, inversely proportional to, so 60% of power flow on that line. So 180, 120. And here 60, this is a 0.3, 0.2. So 60% again here. So 36 megawatt. Yeah. Did I say correctly? Sorry, 40%, so 120. 120, and in this case, 36, so 156. Yeah, so 156, and you can compute that similarly. So this is the result. Flows with economic dispatch. And then, yeah, actually the capacity limit is given here. So 126 and 250 and 130. So let's check the economic dispatch solution. That is this one. So yeah, it is okay. This is okay, but this is not okay. So violated by 30 megawatt. So we need to adjust the generation here and there to satisfy. This is 126 megawatt. So how can we do that? Well, obviously, generators are here, and this exists the line limit. So we need to reduce the generation here. That means the power generator, this should be increased, or that should be increased depending on the price. So let's check one by one. The first case is additional generation at bus 2. And yeah, X megawatt, blah, blah, blah. But for simplicity, 1 megawatt, and see what happens. Again, the power is splitting, 0.3, 0.2, so 60%. So 0.6 megawatt and 0.4 megawatt using this reactance information. That, and so yeah, parallel path, the inversely proportional to the reactance. And okay, so yeah, so our aim is to make it 126. So that means 30 megawatt inverse. So 30, 20, then 50 should be injected, and the sum of these two is 120, and then the 184, 116. Okay. Yeah, so this happens when we increase the generation at node 2. Or you can think of, what about inject power at this node? So 1 megawatt is splitted, again 0.2, 0.3, so 60% here. So 0.6 megawatt, 0.4 megawatt there. And again, we need to make this becomes 30 megawatt, right? So, and then 45 megawatt using this ratio. So 75 megawatts should be injected. Okay, so this plus that is that. So what? Okay. Oh. Okay. So yeah. So node 2 and node 3. And node 2 and node 3, the marginal cost are where? The marginal cost of C is $14 and the marginal cost of D is $10. So what I want to do now is I want to compare these two solutions, whether to increase the capacity of the generation there, or whether to increase the generation there, and check the cost. So yeah, because we already so yeah, 75 megawatt times, what was that? The cost? No, you can compute that, okay? So this redispatching generator 2 incurs this much cost, and redispatching the generator 3 incurs this much cost. This is the economic dispatch cost. So out of these two options, select the one with lower cost, and so the cost of security is this minus that. Okay. Still ad hoc method. If you want to solve it more nicely, then you need to think about, in this case, inject X, inject Y, and see what happens. And depending on X and Y, what is the flow? So whether they satisfy the constraints. And when this is X and that Y, what is the cost? So minimize the total cost by changing X and Y, satisfying the line limits. Will give you using this as much as possible, because again D, C, this is cheaper than that, and the maximum capacity is that much. So the required increase to 75 megawatt. So it does not violate this limit. So if you formulate the problem in that way, you still get the same solution. You know what I'm saying? Okay? You see what I'm saying? Yeah. Okay, so yeah. So this is our solution. So this is the result. This is the dispatch that the ISO will implement. So increase generator D by 75 megawatt, decrease this by 75 megawatt. So yeah, this is decreased by 75 megawatt. It is not still being used. Okay. Any questions? No questions.
교수님, 근데 이거 푸는 방법이 이런 방법밖에 없는 건가요?
So I told you. You can solve it this way. So inject X, inject Y, and using this proposition, you can compute. No. Okay. Yeah. Okay. Inject X amount. Okay. Then this is multiplied by blah, and that gives you so 50 times It's just x, 0.6x, 0.2x, right? And then y, then 0.6y, 0.4y. Anyway, applying superposition principle, just add them up.
제 말은 이제 그러니까 슈퍼포지션이 이렇게 단계별로 하나하나 제약 조건을 맞춰 나가서 맞추는 건데 한 번에 풀 수 있는 방법은 없나요?
So I'm saying, yeah, why not? This is not bad. So x injection and y injection, and using superposition, we can compute additional flow from x and from y, and then we can construct. Actually, you should do that as a homework. Okay? Yeah, there's a homework by Wednesday. Okay, so from here, okay, yeah, this plus that gives this kind of solution, satisfying that. So you need to determine how much to add here, inject here or there, and x. Again, x point 2/3 x, 1/3 x here. Am I correct? No, 0.6x here, 0.4x here. Add and then that should be less than 126. And your objective function is the cost based on the marginal cost of this generator and that generator, $10, $14, okay? And you have constraints, this constraint, that constraint, that constraints. This maximum. Then you have a linear programming problem. You see what I'm saying? You have constraints, you have a linear objective function. Find the way that minimize this, satisfying these line limits, x and y. Then the solution would be that. Are you sure, professor? Yeah, I'm sure. Because the solution is the 75. And we know that the maximum of D is 85. Okay, so this is cheaper than, where is it? This is cheaper than this one. So using the cheapest generator as much as possible, and that solution coincides with that. So this ad hoc solution will be same to your systematic solution. You see what I'm saying? Check it.
저 질문도 있는데
Okay?
저게 결국에는 저 라인 플로우 리밋을 고려했을 때 오버로드 되는 거를 찾아서 거기를 그 오버로드 되는 거의 라인의 맥스 값을 하도록 지금 그렇게 계산이 다 이루어지는 거잖아요. 근데 그래도 되는 건가요? 계속 맥스 값을 만족 굉장히 좀
Okay, another good question. So why do we need to satisfy, or why that constraints need to be binding? That's your question. That's why you need to do your homework. Okay? So, X injection and Y injection, and you have set of constraints, and check it. And the minimum solution, the solution that minimizes the cost, will give you this binding constraint. I think so. Yeah, so please check it. How can you explain it intuitively? Intuitively, so from optimization perspective, economic dispatch solution violates some constraints. Then the way to make it feasible is to tweak the variable so that the violate constraint is met. Anyway, from current solution, this is not a feasible solution. Economic dispatch is not a feasible solution. So you need to change the variable so that it make it to make it feasible, right? And what is the meaning of a constraint is binding? The constraints works. What are you talking about?
근데 수학적으로는 뭐 맞는 건데 이게 제 말은 실제 상황 물리적으로는 항상 라인이 맥스 값을 도달하는 형태라서
So yeah, Okay, so I think your question is that what is the meaning of the physical meaning of this binding constraints in power system? And then if all of these constraints are not binding at all, that means the solution is same to economic dispatch. Okay? That means when there are constraints but no constraints are binding, that means the constraints does not play at all. That means we can think all of the generators and loads are connected in a single bus. Okay? Because the constraint does not play at all. So the binding constraint means that that's the point where congestion happens and the thing happens. And so that's why it is important to, how can I say? Anyway, so interesting things in optimization always happens at the boundary. Okay, if the optimal solution is strictly inside of the boundary, that means we don't need to have that constraint. That constraint does not play at all. That means if you assign a Lagrange multiplier for that constraint, the Lagrange multiplier becomes 0. Okay, that means the penalty to violate the constraint is 0. Okay. So this is your homework that you should turn in today, and by Wednesday you need to do that homework and check the solution is same to that one. Okay. And next topic is calculating the prices at each node. So because congestion happens, the price at each node become different. And so different price is called nodal price, or LMP. Okay, so yeah, that's nodal price. The meaning okay, what is the meaning of SMP? So when we talk about SMP is the marginal cost. SMP equals to the marginal cost, right? So that means when the load increases, we need to pay this much of money to the generator to satisfy the demand. Okay, that's the SMP. SMP is same when there is no congestion in the network. Everybody sees the same SMP. Okay? But in reality, for some line, there are congestions. So different nodes have different locational marginal pricing, nodal pricing. So yeah, this is very well defined statement. So nodal price is the cost of supplying an additional megawatt of load without violating the security constraints. What? So yeah, here we have 3 lines. Suppose that the load here increases, then somebody needs to provide the energy, power, without violating the constraints. Okay, so maybe we can increase the generation, this generation or that generation or that generation to satisfy that. And if that can be possible using the local generator, that would be good. But if that's not possible, no other generators need to satisfy that, need to cover the increased demand, but should not violate the constraints. So maybe we need to use that generator or that generator. And that incurs cost of this generator or that generator. So the concept of nodal price, depending on node, so when the load increase at that node, how can we satisfy that without violating the network constraints with minimal cost? Okay, so this is from the minimal cost perspective that is similar to SMP, but we need to satisfy the network constraints. Okay, so let's start from OPF solution, and let me stop here, and we will keep talking about nodal pricing on Wednesday.